In quantum mechanics, the momentum operator is an operator which maps the wave function psi xt in a Hilbert space representing a quantum state to another function. If this new function is a constant p multiplied by the original wave function psi, then p is the eigenvalue of the momentum operator, and psi is the eigenfunction of the momentum operator. In quantum mechanics, the set of eigenvalues, the spectrum, of an operator are the possible results measured in an experiment. In this case, the possible results of a measurement of linear momentum. The momentum operator is, in the position representation, an example of a differential operator. For the case of one particle in one dimension, the definition is p equals minus I x. Display style hat p equals r hbar frac partial x, where h is Planck's reduced constant, I the imaginary unit, and partial derivatives, denoted by display style partial, are used instead of a total derivative dx. Since the wave function is also a function of time, the hat indicates an operator. The application of the operator on a differentiable wave function is as follows: p psi equals minus I psi x. Display style hat p psi equals r hbar frac partial x. In a basis of Hilbert space consisting of momentum eigenstates expressed in the momentum representation, the action of the operator is simply multiplication by p, i.e. it is an multiplication operator, just as the position operator is a multiplication operator in the position representation. At the time quantum mechanics was developed in the 1920s, the momentum operator was found by many theoretical physicists, including Niels Bohr, Arnold Sommerfeld, Erwin Schrödinger, and Eugene Wiener. Its existence and form is sometimes taken as one of the foundational postulates of quantum mechanics. Origin from de Broglie plane waves. The momentum and energy operators can be constructed in the following way. One dimension. Starting in one dimension, using the plane wave solution to Schrödinger's equation of a single free particle, psi x t equals e I p x minus e t. Display style psi x t equals e frac I hbar pxa closing curly bracket comma closing curly bracket, where p is interpreted as momentum in the x direction and e as the particle energy. The first-order partial derivative with respect to space is psi x t x equals I p e I p x minus e t equals I p psi. Display style frac partial psi x t partial x equals frac I p hbar e frac I hbar pxa equals frac I p hbar psi. This suggests the operator equivalence p equals minus I x. Display style hat p equals r hbar frac partial x. So the momentum of the particle and the value that is measured when a particle is in a plane wave state is the eigenvalue of the above operator. Since the partial derivative is a linear operator, the momentum operator is also linear. And because any wave function can be expressed as a superposition of other states, when this momentum operator acts on the entire superimposed wave, it yields the momentum eigenvalues for each plane wave component. These new components then superimpose to form the new state. In general, not a multiple of the old wave function. 3 dimensions. The derivation in 3 dimensions is the same except the gradient operator del is used instead of one partial derivative. In 3 dimensions, the plane wave solution to Schrödinger's equation is psi equals E I P R minus E T. Display style psi equals E caret frac I hbar. Math BF P C dot Math BF R A. Closing curly bracket, and the gradient is psi equals E x psi x plus E y psi y plus E z psi z equals I P x E x plus P y E y plus P z E z psi equals I P caret psi. Display style begin aligned nabla psi and equals math BF E underscore x frac partial psi partial x plus math BF E underscore y frac partial psi partial y plus math BF E underscore z frac partial psi partial z and equals frac I hbar left P underscore x math BF E underscore x plus P underscore y math BF E underscore y plus P underscore z math BF E underscore z right psi and equals frac I hbar math BF hat P psi end aligned, where x, E, y and Ez are the unit vectors for the 3 spatial dimensions. Hence, P caret equals minus I. Display style math BF hat P equals R hbar nabla. This momentum operator is in position space because the partial derivatives were taken with respect to the spatial variables. Definition: position space for a single particle with no electric charge and no spin. The momentum operator can be written in the position basis as P caret equals minus I. Display style math BF hat P equals R hbar nabla, where is the gradient operator. H is the reduced Planck constant, and I is the imaginary unit. In one spatial dimension, this becomes P caret equals P caret x equals minus I x. Display style hat P equals hat P underscore x equals R hbar partial over partial x. This is a commonly encountered form of the momentum operator, though not the most general one. For a charged particle Q in an electromagnetic field, described by the scalar potential phi and vector potential A, the momentum operator must be replaced by P caret equals minus I minus Q A. Display style math BF hat P equals R hbar nabla Q math BF A, where the canonical momentum operator is the above momentum operator. P caret equals minus I. Display style math BF hat P equals R hbar nabla. This is of course true for electrically neutral particles also, since the second term vanishes if Q equals 0 and the original operator appears. Properties: hermeticity. The momentum operator is always a Hermitian operator. More technically, in math terminology, a self-adjoint operator, when it acts on physical, in particular, normalizable, quantum states, in certain artificial situations, such as the quantum states on the semi-infinite interval 0, infinity, there is no way to make the momentum operator Hermitian. This is closely related to the fact that a semi-infinite interval cannot have translational symmetry. More specifically, It does not have unitary translation operators. See below. Canonical commutation relation. One can easily show that by appropriately using the momentum basis and the position basis, x caret p caret equals x caret p caret minus p caret x caret equals I. Display style left hat x hat p right equals hat x hat p hat x equals r hbar. The Heisenberg uncertainty principle defines limits on how accurately the momentum and position of a single observable system can be known at once. In quantum mechanics, position and momentum are conjugate variables. Fourier transform. One can show that the Fourier transform of the momentum in quantum mechanics is the position operator. The Fourier transform turns the momentum basis into the position basis. The following discussion uses the bracket notation. Let psi equals psi x. Display style psi equals psi x. Closing curly bracket. Be a wave packet. Psi pipe psi. Display style Langle psi wrangle equals 1. Psi single quote. Display style psi. The Fourier transform of psi. Display style psi pipe p caret pipe psi equals h psi single quote pipe x caret pipe psi single quote. Display style Langle psi hat p psi wrangle equals h Langle psi hat x psi wrangle. So momentum equals hx spatial frequency, which is similar to energy equals hx temporal frequency. X pipe p caret pipe psi equals minus I d x psi x. Display style Langle x hat p psi wrangle equals r hbar frac d dx psi x. Closing curly bracket. The same applies for the position operator in the momentum basis. P pipe x caret pipe psi equals I d p psi p. Display style Langle p hat x psi wrangle equals r hbar frac d dp psi p. Closing curly bracket. And other useful relations. P pipe x caret pipe p single quote equals I d p delta p minus p single quote. Display style Langle p hat x p wrangle equals r hbar frac d dp delta pp. Closing curly bracket. X pipe p caret pipe x single quote equals minus I d x delta x minus x single quote. Display style Langle x hat p x wrangle equals r hbar frac d dx delta xx. Closing curly bracket. Where delta stands for Dirac's delta function. Derivation from infinitesimal translations. The translation operator is denoted T epsilon, where epsilon represents the length of the translation. It satisfies the following identity. T epsilon pipe psi equals d x T epsilon pipe x pipe psi. Display style T var epsilon psi wrangle equals int dxt var epsilon x wrangle Langle x psi wrangle. That becomes d x pipe x plus epsilon x pipe psi equals d x pipe x minus epsilon pipe psi equals d x pipe x psi x minus epsilon. Display style int dx x plus var epsilon wrangle langle x psi wrangle equals int dx x wrangle langle x var epsilon psi wrangle equals int dx x wrangle psi x var epsilon. Closing curly bracket. Assuming the function psi to be analytic, i.e. differentiable in some domain of the complex plane, one may expand in a Taylor series about x psi x minus epsilon equals psi x minus epsilon d psi d x. Display style psi x var epsilon equals psi x var epsilon frac d psi dx. So for infinitesimal values of epsilon, t epsilon equals 1 minus epsilon d x equals 1 minus I epsilon minus I d x. Display style t var epsilon equals 1 var epsilon d over dx equals 1 I over hbar var epsilon left I hbar d over dx right. Closing curly bracket. As it is known from classical mechanics, the momentum is the generator of translation. So the relation between translation and momentum operators is t epsilon equals 1 minus I epsilon p caret. Display style t var epsilon equals 1 I over hbar var epsilon hat p. Thus p caret equals minus I d x. Display style hat p equals I hbar d over dx. For momentum operator, inserting the 3D momentum operator above and the energy operator into the for momentum as a one form with plus minus 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 metric signature p mu equals e c minus p. Display style p underscore mu equals left frac e c math bf p right. Closing curly bracket. Obtains the for momentum operator p caret mu equals 1 c e caret minus p caret equals I 1 c t equals I mu. Display style hat p underscore mu equals left frac 1 c hat e math bf hat p right equals I hbar left frac 1 c frac partial t nabla right equals I hbar partial underscore mu, where mu is the for gradient and the minus ih becomes plus ih preceding the 3 momentum operator. This operator occurs in relativistic quantum field theory, such as the Dirac equation and other relativistic wave equations. Since energy and momentum combine into the for momentum vector above, momentum and energy operators correspond to space and time derivatives, and they need to be first-order partial derivatives for Lorentz covariance. The Dirac operator and Dirac slash of the for momentum is given by contracting with the gamma matrices. Gamma mu p caret mu equals I gamma mu equals p caret equals I slash. Display style gamma caret mu hat p underscore mu equals I hbar gamma caret mu partial underscore mu equals hat p equals I hbar partial backslash exclamation mark slash closing curly bracket. If the signature was minus plus plus plus, the operator would be p caret mu equals minus 1 c e caret p caret equals minus I 1 c t equals minus I mu. Display style hat p underscore mu equals left. Frac 1 c hat e math bf hat p right equals I hbar left. Frac 1 c frac partial t nabla right equals I hbar partial underscore mu. Instead, see also mathematical descriptions of the electromagnetic field, translation operator, quantum mechanics, relativistic wave equations, Pauli-Lubansky pseudovector.